Thank you. Yeah. This talk is gonna be about Android and its full disk encryption. I had an introduction, so there's not much I'm gonna say about myself. I work on security. I do security audits, mostly code audits, nothing breaking into facilities and stuff like that. And I also do engineering work, so I have both hats on, and I also have a third hat, which is managing other people and so on. So there's a bunch I do, and at one point I got this request from a person. Sorry, slides are messed up. I got on social media. I got a message from saying, "Hi, somebody told me about you. It's a friend of ours. I know that guy. Can you help me recover data from my Android phone?" And I was like, "Yeah, well, sure. Do you have a backup?" They were like, "Yeah, sure, but it's a low-level disk dump and it's encrypted." And I was like, "Okay, well, I have more questions." But on the other hand, there was this little voice in my head and said, "It's a new toy. It's something I'm gonna could have fun with." So long story short, I met up with the guy. We talked about it, and he told me his phone is some Samsung flagship phone at the time, was stuck in a boot loop. So he got into the bootloader, created a disk dump, low level from the bootloader side, and then he flashed Android 12 on there. The thing was running Android 11 before, and now it's running Android 12, and it's working again. I was like, okay, maybe, yeah, I can have a look at it, and I can try, maybe see if we can decrypt that. So, in the sense, I was thinking, this is somehow like an evil mates attack, right? Because I have physical access to the phone, and I want to recover the encrypted data that's on there, but now it's just not on the phone itself, it's in a backup file. But in the end, it doesn't really matter. And I also have the advantage that I have the passcode which he gave me. And I don't need to care about being stealth and him not noticing me. So in the end, I have a bit of an easier task, but not really. What I knew at that time was that Android's disk encryption feature is called file-based encryption. That's their marketing term since Android 10. And they do basically use the Linux stuff for disk encryption. So they use the mcrypt, they use fscrypt, which was actually created by Google and upstreamed. So in the end, it's what I knew. I worked with that stuff almost daily. So I knew that part. And the easy part with disk encryption is all you need is the key, right? You just need the key, then you can give it to the kernel, and then it will decrypt everything for you. Yeah, I knew that there has to be some security chip or trust zone stuff involved, because otherwise it wouldn't make sense, because then it wouldn't be secure. And I didn't know how Android was using that, and I didn't know a lot about the details of that. I also knew that maybe the passcode would come into play at some point, or biometrics. Yeah, and I thought it was time to change that. I wanted to know more about that. So the first idea was, I have a backup, and he told me it's stuck in a boot loop, so why not just flash the backup onto the phone and be done with it? Yeah, I tried that, and I noticed that I couldn't flash Android 11. I couldn't flash an Android 11 backup on a device which was now running Android 12, because Samsung flipped some bit in the low-level efuses, which told the phone it wouldn't allow flashing an older version. So that was downgrade prevention, and the reason for that was, after I searched for it, and I got a hint, the reason was a paper which is called Trust Dice in the Darkness, shedding light on Samsung Trust Zone keymaster design, which was exactly, after reading the paper, was exactly what I would have needed, because they found a flaw in the trust zone mechanism that's doing the decryption of key blobs. And that's the whole thing which brings the security to disk encryption on Android. So, tough luck. But there was one cool thing. The guys who did that, they published their tooling, so it's on GitHub, and I could look around, and I saved a lot of time on reverse engineering. So I thought, hey, let's make it easy. Let's live off the land. Let's use what's there. I have an Android 12 phone. It's running. I can simply root it. That worked fine. It has to somehow work, I thought, because during an upgrade from Android 11 to 12, the same thing would happen, right? So it should be able to deal with a disk that's encrypted for Android 11. But what I didn't know is, since he flashed Android 12 on there, if something was reset and I couldn't recover those key blobs that were on there. And I also didn't know what Samsung changed, and they do not tell anybody about it, because I got access to the GPL resources from Samsung, but and also the Google sources, so the official upstream Android source, but I don't know any user space code which Samsung doesn't publish. So there could have been or could be something in there which I'm missing. So I did quite some research. I read up on how Android works. I searched through the upstream Android code, and basically Android, since Android 9, does disk encryption in 3 layers. There's metadata encryption, which is the lowest. Then there's device encrypted storage, and then there's credential encrypted storage. Metadata encryption is basically quite similar to what we have, or almost the same as the Encrypt on Linux. So it simply takes, it sits in the block layer, so the file system sits on top of that, and everything the file system wants to write to disk is passed through the block layer and gets encrypted and then written to disk. It needs a single key, and there's some I/O controls for setting that up, for setting the key, and then you're done. It's called DM default key for some reason, but in the end, if you look at the source code, it's almost the same as the Encrypt. Then there's device encrypted storage, which is the second layer, which sits on top of that. This storage is only, they do encrypt only parts of the partition, so it's just some folders. And it's available right after boot, so you don't have to enter your passcode for that. And the device will automatically open up that encryption layer and have it accessible on the device. It's used for, I think, phone calls, alarms, and stuff like that. It's using FSCrypt, which is, as I mentioned before, which is an encryption layer which is upstream in the Linux kernel, and it sits right in the file system, so the file system has to support it. Gstir, F2FS, and UBIFS and others do support it. I know that stuff because I've upstreamed part of that. And there's simply one I/O control which you can use to set the key, and the rest just works. If the kernel supports it, then it should. And then there's the last one, that's credential encrypted storage. That's the first part when you need your passcode or your fingerprint or whatever. It again uses FSCrypt. It's basically the same thing, but it factors in your passcode somehow. And the somehow is the interesting part. And also it will use the trust zone for that. So the high level boot logic after looking at the source code is something like that. The kernel goes ahead, mounts /metadata, it finds a key on there, it unwraps it using the trust zone. Then it attaches that device mapper volume using the DM default key. Then it goes ahead, mounts that, looks up more key blobs from there, which is the DE key, so the device encrypted key, and the CE key. And both are again unwrapped using the trust zone and added to the kernel via the FSCrypt I/O control. And then you're done. So all I had to do was re-implement that for the backup file which I was attaching, and that should work. Yeah, there's one key part or key element which is involved there, which is the trust zone and which handles the trust zone, and that's called the Android key store. The Android key store consists of multiple parts. There's user space part, which is the key master HAL, so hardware abstraction layer, I assume. And there's a key master trusted application, which is running in the trust zone. So on Samsung phones, I think it's called Tigris, their trust zone OS. And the keymaster application is implemented by Samsung. It's closed source. You have to reverse engineer to really find out what it's doing. But in the end, the paper I was reading, and I was mentioning before, they did a bunch of reversing there and found the bugs. And they also had some cool tooling. And also I found the trick from them, which is their tool, which they called Gstir. They were not directly talking to the user space daemon, but instead they used the shared library, which this daemon was loading, to bypass all the checks the user space daemon was doing. Because the daemon was checking who is calling me, who wants to decrypt the blob, but the shared library didn't. So I could just go ahead and use the shared library directly and then talk to the trust zone side. So the high-level picture is something like this. You can ignore the gatekeeper parts for now, but the key store, and there's something called volumd, so I assume volumd, so vault, which is the main service which does all the setup during boot. And it's talking to the key store, which is then talking to the keymaster, and I didn't draw it here, but the shared library sits in between here, and it's talking to the kernel interface for the trust zone. On the trust zone side, we have the trusted applications like the keymaster. And there's also the kernel implementations for the file systems, which I have to call the iControls tool to set the keys once I got them. Yeah. Long story short, I had to really dig through the Android source code to find which keys are loaded and when, and some things were a bit different on Samsung phones. But in the end, I found that the metadata key is loaded from that path. I looked there, there's a bunch, I could mount that from the backup directly because that partition is not encrypted at all. There's a bunch of files in there, and looking through the code, I noticed I can ignore some of them, like the stretching file, which contains no password, and when it does that, I can simply ignore that file, which was the case for me, so lucky. The sec discardable file is some number or some random thing which you just use, pipe through a hashing algorithm, and then you get something that they call app ID, which I only need to send to the keymaster, to the trust zone application, and that should work. And there's two keys, or two encrypted keys. The encrypted key itself is the key I want to get, and there's the keymaster key blob, which is basically a key encryption key. So what they do is they encrypt this encrypted key using this key in there, and this key itself is encrypted with something the trust zone has. But I didn't know what it was. So my idea was to simply do the usual process. I give everything the trust zone needs to the trust zone and let it do its thing, and hopefully I get the plaintext key back. Yeah, I did further research and looked into the whole API, and in the end it's three things I have to call on the trust zone side. It's a begin operation, it's an update operation, and a finish operation. The begin operation gets this keymaster key blob, and a bunch of parameters, including the app ID. I get an operation handle back, and then with this operation handle I can call update operation, give it my actual key blob, which I wanted to decrypt. And then I simply get the plaintext key back, and the finish operation is just some cleanup. Then I was looking into the actual shared library, because the Keybuster tool wasn't using these calls. For their stuff, they could use some other APIs, so they didn't reverse those. And then I had to reverse these three functions. In the end, most of the parameters they are getting, I could ignore. And so the simple pseudocode of what you need to do is this. You just read this sec discoverable file, generate the app ID, which is some hash function, but you can look that up in the Android source code. Read the two key blobs, and generate some input parameters. I will get to that. And then I can call the three functions begin, update, and finish. I tell the trust zone that I want to decrypt that key. Here's the encryption key. The parameters, I will get my handle, and then I give it the key blob, which I wanted to decrypt. And then I will get the plaintext key back, and finish is just to not have my program crash. Yeah. The input parameters are basically telling the trust zone what cipher to use, what parameters it needs to decrypt the blob. I have to get those right, because otherwise I will get an error from the trust zone back, which I had a bunch of times. But in the end, if you get everything right, then it will work, and you will get a key back. And so I managed to decrypt, to get the first key blob decrypted. To test that, I had to attach the device mapper volume, which with some minor tooling I managed to do. I had to do some trial and error, but in the end it worked. There's some minor difference between 11 and 12. With Android 12, they added some prefix to their blobs. I could just strip that, and that worked. And there were some bugs in the keybuster tool. They got some constants wrong, but in the end, it worked out fine. So yeah. Then the next layer was the device encryption part, which I thought, yeah, simple, again, do the same thing. It almost was. I was looking for the keys again, and I found 3 keys, which is the data unencrypted key, then there's the DE key, then the CE key. At first, I couldn't read those directories, until I noticed I have to first load that key blob, then those, because that folders were again encrypted with fscript, so there's actually a 4th layer, which they don't tell you about really. But in the end, I could load those key blobs again. I get them decrypted via the Trust Zone API. Some minor issues were there, but nothing really. It's just me being silly and not getting the API right. But in the end, that worked. So what I ended up with was I have basically decrypted the whole file system except the credential encrypted storage. And that's where all the user data actually sits. So all the user data for the user profile is in there. And that's where I want to get to. But in the end, I could boot basically I could load everything from the application. I saw, from the OS, I saw logs. I saw when the device was last booted. I saw basically everything from the system. And everybody can do that with access to the device. You don't need a lot of fancy thing. Basically what I needed was the device and the ability to root the device. And I also knew that flashing Android 12 on there didn't reset the trust zone or any state in there. So it's basically always using the same key. And from what I think, it will keep using the same key. So once you update your phone, it will not change the internal key in the trust zone. And I assume it's hardware bound for some reason. So the next challenge is getting into the credential encrypted part, which will then require the passphrase, which will need a little more work because there's more trust zone stuff in there. It involves another trust zone application, the one which you saw in the picture before. It's called Gatekeeper, which does verify the passphrase roughly. But I'll get to that. I was lucky again because before I started, there was nothing really much on the topic, but quite some time into, I was working on that, and I did that on the side. The brilliant people at Quarks Lab posted on their blog a very similar thing to what I was doing. They were looking into getting the encryption keys. Actually, they were trying to brute force the passphrase, the passcode of Android phones. And they were looking into how to do that using the disk encryption part. And what their approach was, they patched the whole boot chain to get into the trust zone and patch the gatekeeper application, patch the keymaster, and then be able to brute force the passcode and try it, basically. They have brilliant documentation on the blog post, and in the end, that's their picture. What I was doing was that, and that's still to do for the credential encrypted storage. There's a bunch of stuff with a so-called synthetic password, which is derived from the user credentials, and which you need to get the keymaster application really to decrypt your key blob. So the next steps would then be to authenticate the gatekeeper, get the authentication token, which is what Gatekeeper is for. There's a fun thing which the Quarks Labs people noticed. all you have to provide to Gatekeeper is some passcode which works, right? So I have to give them the expected blob, which is encrypted, and I have to give them my passcode, which matches that blob. But I hope I can use that from the Android 12 installation, where I have set the passcode, and I do not need to use the one from the backup. So actually, on that step, I can bypass the passcode, because all they do is they just generate a random authentication token, which is not dependent on the input I gave it. This is called, the output is then called application ID, and with that I can go ahead and have the synthetic password, which is again just a file on the disk, which is encrypted by the trust zone, give it to the keymaster application with that authentication token, and then it will give me a decryption of that synthetic password, which again have to decrypt. So there's two encryptions in there to get the real synthetic password out of it. And with that, I can derive my app ID, which is now different than from what I was using until now, and give it to keymaster, just like I did with all the other layers before. And then I get the actual key, which I can use for fscrypt. Yeah. Now you think, yeah, I did that and it's done. No, I'm not. I haven't. My evil plan here is to get into next year's session, because I haven't finished that part yet. I still have to reverse engineer the Gatekeeper interface, and then I can do all that, which I was telling you about right now. But maybe next year there's going to be a talk on the second part. Yeah, in the end, what I wanted to show you is even if the device looks broken or the backup is encrypted, you have a good chance into getting to your data by simply trying to understand how the system works, how Android is using the trust zone, and with the way it currently is, and I think recent Android versions do the same thing, unless you have the latest security chip variant, which is a bit different. But in the end, you can, as long as you control the device, you can get it to do what you want. And that's the main danger of rooting your password, and your phone will warn you about it. If you use a rooted phone, you should not put any data which is sensitive on there, because you can get it out. The only thing that's stopping you is the passcode. But hey, who enters your passcode in public, right? Nobody does. Okay. Yeah, that's it. Any questions?
We're at the first question in the audience, please. By the way, how did you make sure that the phone you got wasn't from a criminal, that it was just stolen the phone?
That's the reason why I wanted to meet the guy in person. He was actually living close by, so I told him, yeah, come by, tell me, and show me what you have. I even saw the bill which he was using, so I had some checking, and also the friend he was telling me about, I checked with him too. So yeah, I was pretty sure.
Thanks for the interesting talk. Question, do you think that the enclaves that MacBooks, for example, have, or the new ones, I think, with Intel, do you think that any of this is actually secure, or will there be also a similar way to decrypt things if you have the physical access to the device?
I mean, the main problem, in my opinion, here is that the whole decryption of the key blobs does not depend on the state of what's running on the device, right? So I rooted the phone, and I was still able to access the trust zone, and it used the same keys. So they did not factor into their decryption logic the state of my normal world in ARM speak. So I think if you manage, or if MacBooks and other devices actually incorporate that information, then it's a lot better and a lot safer, because then you cannot decrypt everything unless your device is in a secure and verified state. And I think with TPM chips, that's basically the thing, right? You only get stuff out of the DPM if all the PCR values match. I don't know about Macs specifically. They have a dedicated, from what I know, it's a dedicated chip on the system, but I don't know the interface. I haven't looked at that very closely, to be honest.
Any more questions? Then I would say, thanks again, David, for his presentation.
Thank you.